I'm actually embarrassed by this title. It's certainly bombastic. But then again, the Economist has a cover that says that we live in a post-truth era. So it might be more appropriate a paper about the provenance of bullshit, but I'm not an expert. I mean, I'm just the occasional user. So, so let's see what we can say about precise things. I'd like to point out that this, at least the form of this presentation comes out of work that I did here, and very much the influence of Erich Gradl, with whom I work. But it follows some work with a lot of people that was in the realm of database theory. But I hope that today's presentation will be, which is geared toward logicians, will not necessarily need motivation from database theory, I hope. So the truth in the title of my talk is not about validity. That's, hard. It's just truth of model checking, and in fact, as you shall see, truth of model checking in finite models. So consider, a finite model here. And the way we think of it here is that some sort of collection of information items, by which I mean both, let's say, relational facts and absence of relational facts, negations thereof. And then we have a sentence, phi, and this sentence in this model may end up being true or may end up being false. And our interest is in seeing how that happened. So again, from the motivation in database theory, we think of, we use this word provenance to understand, to actually make this question, how that happened, a little bit more precise. So people can and did look at questions such as which information items in the model made the sentence true, are used in the checking. That's fairly boring, but a more general question is, why did it so happen? And the reason this is more interesting is because there may be alternative reasons why the sentence ends up true in this model. And these alternative reasons can be exploited, as we shall see. And what I will actually show is sort of a very general provenance analysis of truth, which answers the question, how is the model information, how is it really used to check on the truth of phi? And we shall see this a little bit more clearly. So the first thing we need to do is, and I should apologize for the low quality of my slides, because this was put together rather quickly. It's basically LaTeX to PowerPoint, I'm sorry. So the idea is that when you actually evaluate or determine, check a sentence in a model, there are two different ways of using the information to establish the truth of that sentence. There are joint ways and alternative ways. And the joint ways, for example, come into play in reasoning about conjunction or universal quantifications truth. Alternative ways, disjunction and existential quantification. And the idea is that we are going to consider non-logical, non-standard interpretations of these concepts in some sort of algebraic structure in which we have two binary operations, one which we denote with dot and the other one with plus, that roughly correspond to these two different ways of understanding and using information. And to see how different this is from the usual logical reasoning, think, for example, that you want to cost the truth of this sentence. So you are adding costs whenever you use information jointly, but then you're choosing the minimum cost when you have alternatives. It's one way, and in fact, it will correspond to something that we use. So notice then, so these are, as you recognize, the usual transformations that we use for putting a sentence in pre-next normal form. So the first two are not at all clearly holding. So look at this, for all x phi and psi. So what may happen is that I will have some cost of establishing psi, and separately some cost of establishing phi for all the x's that I care about. But then if I write it like this, then the cost of establishing psi is repeated. In fact, for every x, even though x doesn't occur there, but it's not relevant. Similarly, this one is also arguing in the same way, not necessarily an equality. With existential quantifiers, there is this particular transformation from existx phi or psi to existx phi or psi, and this one can be thought of as holding, but if you think about it, it's just because minimum is idempotent, because you still actually repeat potentially the cost of, well, when you want to establish an existential quantifier, you just need to do it once, right? And here, of course, you may end up repeating the cost of psi, but because min is idempotent, it doesn't matter. On the other hand, in all the interpretations that I could think about, this one particular transformation does hold, namely pulling an existential out of conjunction. It's possible, and it's debatable, whether that there will be interesting interpretation which doesn't hold, but for the moment, that's not the case. So if you think about all these things hard, what you end up with is an algebraic structure that corresponds to what's called a commutative semiring. And that's our non-standard interpretation domain for logic that we shall play with. So k plus times 0 and 1. So there are interesting commutative semirings in which we can actually say things about logical truth, again, in interesting ways. So just a bit of terminology. We say that the semiring is commutative when multiplication is commutative, but we say that it is idempotent when addition is idempotent. That's just tradition in that area. Of course, the Booleans are the basic commutative semiring. Natural numbers are a commutative semiring. This one is of great interest in what's called bag semantics in databases, but I shall not get into that today. This is a semiring that these two semirings, which are isomorphic, I will talk about, and they are well known to many people in the audience. So this one is, let's say, thinking about the cost that I mentioned on the previous slide. It's called the tropical semiring for bizarre reasons. And here the plus is min, and the times is plus. So you have to keep your things straight as you reason about this tropical semiring. But it's maybe easier to sometimes to think in its isomorph, which is called the Viterbi semiring, because something like this was used in certain dynamic programming algorithms in reasoning about decoding and so on by Viterbi. In determining, for instance, path of maximum likelihood. So the times that you see here is about multiplying probabilities because there are some independence assumptions, and the max is about finding the path of maximum probability. But the way I will think about this semiring is all these numbers are confidence coefficients, confidence scores, and the closer to 1, the higher the confidence I can have in this. And the two are actually isomorphic, so I can think about the cost as the cost of screwing it up. So the higher the cost of screwing it up, the less confidence it means you have in that particular fact. This one is a distributive lattice. All distributive lattices are, in fact, of course, commutative semirings. But this one is just a very simple one. It has 5 elements. I order them like this, and I take min and max. And this one, let's call it access control. If you think of these things as levels of access control, such as public, confidential, secret, top secret, and there's one at the very top, so secret that nobody can access it, so we don't know about that stuff. It's not there. Then this would allow us to reason about access control, and I shall have at the end an example. There's been a lot of mathematics called fuzzy mathematics that's been done in this semiring. I don't have anything special to say about it. But here is a really, really interesting semiring in which we shall actually do a lot of reasoning about provenance. And that's the semiring of polynomials. The coefficients are natural numbers. The rest is just plus times usual. And the polynomials have they are multivariate polynomials. The indeterminates are from some set X. And I shall think of this set X as labels, or in fact, the terminology I like is tokens that I annotate to facts of interest. And then I use these tokens and what happens to them to track the provenance of those facts of interest through the model checking. And this, by the way, is a commutative semiring freely generated by the set X, and that's going to be used in the good compositional and categorical way that it's the only way we know how to do things, right? And another one is Boolean expressions. This one, by the way, if you recall, the talks about probabilistic databases are used under the name lineage in trying to compute probability for queries. All right, so let's do something different now. So suppose we have a finite relational vocabulary, and we have a finite set of ground values and not yet a model. So I'm going to talk about sentences without having a model. It's a little weird, but you will see what the benefit of doing that will be. So let's denote by facts the set of all ground relational atoms with R from this vocabulary, and this is some vector of ground values. And let's denote with negative facts, the negated facts. And as we use in logic programming, let's call the union of these two literals. So these are those information items in the model that I care about. And I'm going to, as you shall see, eventually label them, annotate them with these provenance tokens, and see what happens in the in the checking of a sentence. Now, an interpretation for a semiring K, a commutative semiring K, and the terminology I'll use, a K interpretation, is absolutely simply a mapping from the literals to K. So I'm just associating to every literal an element of the semiring. Whether provenance or cost or confidence or access control, whatever, all those things will be things we can exploit. But I shall say, like right now, that very roughly, the idea is that the zero of the semiring is going to be used to interpret things that end up being irredeemably false, and not zero things that will be true. And now notice that we have a lot more nuance in the interpretation of truth, because there will be, of course, in the Boolean semiring, there's only one thing that's not zero. That's true. But in all these other semirings, we have a lot of nuance in interpreting truth at various other elements in the semiring, and let's see what that gives. So this first thing that we can say is that, let's say that an interpretation is consistent if the product of the interpretation of a fact and its negation is zero. The semirings in which, all the semirings which I showed at the beginning, have a property, it's called positivity. And the semiring is positive if it satisfies these two properties. A times B is zero. That means that either A or B is zero, and A plus B is zero. That means both are zero. Let's sort of think natural numbers. And it turns out all the semirings that I've shown earlier are positive. Semirings which are not positive are basically rings, like the integers, or the integers, mod 2, the Boolean ring. And but it's not clear what the interpretation in those particular semirings would give us. And so I have nothing intelligent to say for the moment, but who knows? So in a positive semiring, when I say the interpretation is consistent, one of these two must be zero. So that's good. I'm not going to make both of them potentially true. And, well, this is a little ambitious to call this complete, but, that's what the terminology is in logical theories. So we say the interpretation is complete if their sum is not zero. So that means that they can't both be zero. And in fact, If we take this interpretation, we can now extend it to all first-order formulae. In the obvious way, of course, for the literals, in the way that I hinted at for the conjunction is multiplication, disjunction is addition, existential is just finite sums, so it's not clear what this all means outside of a finite model, but who knows? There are semirings in which infinite sums exist. And for universal quantification, it's a product. And this is the trick that Erich really, I had a lot of trouble with negation, and those of you who were at my first talk in August recall that I was just throwing my hands up, but Erich actually helped me see the light. And his suggestion was, well, let's look at negation normal form. So that's kind of punting on the issue, right? Interpreting negation or subtraction in general commutative semirings, in other words, finding an operation in the semiring, yeah, not plus or times, yet a third unary operation that somehow captures the idea of negation is hard. I mean, of course, in Boolean algebras we have it. But for natural numbers, what is it? There is something called monus, and so there is no nice theory, and there are multiple divergent ways of dealing with this, and very annoying. So negation normal form actually allows us to essentially punt on this. That this is a term from American football, but in terms of European and football for the rest of the world, just means to clear a ball from your box of 18 and get it out of there. So now things actually become very nice. So look at this. Well, the interpretation of double negation is the same, and De Morgan as well, So negation stops being a problem, so we can focus on the difference between conjunction and disjunction. So the first thing we can do, since I talked about consistency and completeness, is to say, well, if K is positive, then consistency and completeness lift to entire formulae and sentences. This is like a basic sanity check. So in a positive semiring, if the original interpretation of the literals is consistent and complete, then you look at the interpretation of some formula phi and its negation, and you just know that one of those two is different from 0 and the other one is 0. So it's sanity check number 1. And sanity check number 2 is, well, consider a model, and there is a canonical interpretation, of course, for that model, namely the literals which are true in the model are going to be top, true, and false, and then the model checks that sentence if and only if the interpretation gives us true. So there's nothing bizarre here. It starts from stuff that we understand, but where does it go? And this is where it becomes somewhat more interesting. So I'm going to build a semiring in which we can talk about provenance, whatever we shall see that means. So the provenance tokens, some set of provenance tokens X, because I want to deal with both positive and negative facts, it helps actually to make a copy of it. So X and X bar are going to be disjoint sets, but in bijection. So I'm going to use P for a provenance token for a fact, and P bar for that same fact negated. And I'll better make sure that not both of them are at the same time non-zero, right? Okay. And what I can do is I take that semiring of polynomials and I can quotient by all these equalities, P times P bar equals 0 for all the P's in X. And the result is essentially the set of polynomials in which in no monomial do we have both a P and a P bar. But a P and a P bar may occur in different monomials of the polynomial. So with this, let's spend some time, on an example. I think this is where we can understand best what's going on. So here is a sentence that says that in a graph, the vertex X is, I just made this up, is dominant. I don't think that people use this terminology. But I need a simple example. So what does that mean? For any other vertex, either it's the same, or For any other vertex, there is an edge from x to y, but there is no edge from y to x. So these dominant vertices have edges to everybody else, but nobody has an edge to them. It's not an unreasonable name. Notice I skipped over this, but notice that we can throw into this logic easily equality and non-equality. It's just not a problem. The interpretation of these things will always be 0 or 1. So a moment, just take a moment to describe the interpretation of what 0 and 1 means. So 0 means it's not there, doesn't exist, false, blah, blah, blah. But 1 is more interesting. 1 is from a provenance perspective, 1 is the interpretation of a fact that I want to take for granted, that comes for free, that I choose not to track. Whenever I need to use it, I can use it, and it's just not something that will affect my otherwise analysis of provenance. So that's the meaning of 1. Okay, so then I take the sentence that just for fun, I'll consider also its negation. For all x, there's no dominant vertex. And these examples can get pretty big, so I'm just going to consider a very small set of 3 ground values. So this is about graphs with just 3 vertices. And I'm going to use some provenance tokens. And remember, the provenance tokens will be for facts like E of, say, A and B. And therefore, they are going to be for the presence of some edges, these ones, and these ones for the absence of some edges. But I'll use the word potential here because in this provenance analysis, I will actually track both. And then I'll make sure that I'll never actually assume both the presence and the absence of the same edge. So, this example, it's always better to think of it graphically. So to ignore all that stuff. So look at this particular set of edges over A, B, C. So here, for this edge, which is the edge from B to A, I'm going to use the provenance token T for its potential presence and T bar for its potential absence, and so on. These ones which are dashed, notice that there's a 0 and a 1. So these are edges which for sure are absent. So the provenance of their presence is 0, and the provenance of their absence is 1. And I thought I should, and there's others which I'm not drawing here, okay? And this is now an interpretation in that particular semiring that I just discussed earlier, in which I just attach to literals P, P bar as we discussed, and everybody else, 0 for all the other positive facts and 1 for all the other negative facts. So the calculation that I can do now in this semiring of the provenance of that particular sentence, phi, which says for all x not dominant of x, is the following. So first I put it in negation normal form because it's the same thing. And then you have to trust me, we don't have time to go through this. You just get to these 3 polynomials multiplied. I'm not going to multiply these 3 because, there's a lot of stuff coming out. So notice that whenever I multiply P bar with P, that monomial is going to go away because P times P bar is 0. So there should be, if I counted correctly, 34 monomials in this provenance. And I call such polynomial one version of what we could call provenance, right? What does it mean? Well, let's look at a couple of the monomials. So ST is somewhere in there. P bar, Q bar, R is somewhere in there after multiplication. So recall now that ST is actually saying there's an edge from, S has an edge from C to B, this one, and T says an edge from B to A. So I can think of the presence of these edges as denying the dominance, right? So this one denies the dominance of B, this one denies the dominance of A. So just knowing that the dominance of A and B is denied should be enough for me to prove that there is no dominant vertex. You may ask, well, how about C? Well, it turns out that the dominance of C the non-dominance of C comes for free. Why? Because I know there is no edge from C to A. That's assumed. So what's really important is that this thing here is a bunch of tracking provenance assumptions that you make at the very beginning. So under these assumptions, we can do a certain amount of reasoning. If you need to reason about things which are not captured by these assumptions, then you need to change these assumptions. So that's the limitation of the framework. So for this one, I actually drew for you a proof tree. We're not going to try to decode it. We don't have time. So this is the proof tree that there is no vertex dominant. That's a lot of abbreviations here. That uses the fact that, well, there's no vertex from A to B, there's no vertex from B to C, and there is one from C to A. So this one denies the dominance of A, this one denies the dominance of B, and this one denies the dominance of C, which gives you this proof tree. So in fact, the provenance polynomial I've just shown you actually counts all the proof trees, and there are 34 of them. So one way, and describes them too. So one way to, and I shall also hope that you believe.
So the number of monomials, right?
Yeah. So each monomial corresponds to a distinct proof tree. Okay, so if you are interested in how many ways you can check this thing, in exactly 34 ways. Well, the polynomial that I have there is not so interesting, but you can get things like coefficients of more than one, is an example, and even exponents, which I will skip. And let me also compute the provenance, because I need it for an example, of the negation of that same sentence. Namely, there exists a dominant vertex. This one is a lot simpler. It just has two monomials. There are only two ways to prove that, that in fact there exists a dominant vertex. This one makes A dominant, the vertex A, and this one makes the vertex B dominant. There's no way to make vertex C dominant under those tracking assumptions. So how hard is compute this provenance? Just some cheap complexity remarks. The provenance expressions have size number of ground values at the size of the formula. But if you put it in polynomial form, it's like putting in normal form Boolean expressions, this may be exponential also in A. Think this example. However, for the database relevant things where you don't have universal quantification.
Oh, sorry.
Yeah.
Dumb question. I missed something.
Please.
I thought you had 34 proofs that nothing was dominant and 2 proofs that something was dominant. What did I miss?
This sentence is the negation. So this is the sentence that says something is dominant.
And you have 2 proofs?
And I have 2 proofs of that, except in each of the proofs, other vertices are dominant. So in the first proof, P makes A dominant, R makes B dominant, T bar makes, no, it's more complicated than that. P and T bar are needed to make A dominant, and
okay.
yeah. So A is dominant. Okay. In the second one, B is dominant. Yeah. So in fact, P, R, and T bar are all needed to make A dominant.
I think what the question really was is, you're proving 2 contradictory things, but you're proving them from contradictory hypotheses.
Yeah, so these are 2 different proofs.
The proof,
On the
these
previous
2,
slide.
Yeah, these are contradictory. That's right. So that's because, well, so that's the nice thing, the interesting thing about this provenance analysis like this is that I can't have both P and P bar be true. So in any given model, yes, only one of these 2 monomials is going to be realized. So, and I think you can compute the number of proof trees. So finally, what is the sanity check number 3? It's right here. So if K is positive and you have what we call an interpretation that's, let's say, truth compatible with the model. Namely, the literals which are made true by the model are mapped to something that's not 0, and those which are made false by the model are mapped to 0, then you actually get that the sentence is true in the model if and only if it gets a non-zero interpretation, and that's in every, so it's like a cheap sort of sanity check. The interesting thing is, to prove this, actually, we prove something much more important, which I dare call the fundamental property, which is right here, and I should have really put some diagrams here. So what is it? It gives you a comparison between what happens in two different semirings if you have a homomorphism between them. Suppose you have homomorphism, suppose you have two interpretations related by that homomorphism, then any sentence, when you interpret it in the two different semirings, will be related by the same homomorphism. And in fact, well, I'm going to skip this because I don't have time, but what you have here is a proof using this of that sanity check number 3.
So the Boolean semiring is the terminal.
It's like your baseline truth.
Yes, it's the terminal object in the character
Yes.
positive semiring.
Right. That in itself, I don't know how to use, but the homomorphism, I mean, the homomorphism itself that takes me there, I use. Right. So I know I'm over time. You're being very patient. So confidence maximization, and then something about access controls, because really this is where we get mileage out of this. So let's look at the negation. I had two sentences, phi and not phi. Let's look at this one. And let's try to interpret it in the Viterbi semiring. Suppose that I map absolutely every provenance token to 1/2. That corresponds to actually assuming some, for lack of a better, a confidence of 1/2 for all my facts. I know this is not consistent, because I'm mapping both P and P bar. I know this is not consistent, but I'm going to be saved by the inconsistency from the fact that I'm looking only at distinct monomials. And in any monomial, by my construction, there will be no inconsistency because there will be no monomial in which both P and P bar can occur. So then, if I look at this proof and at this provenance and interpret it, and the whole point of the fundamental property is that you can do the provenance in general, then you can interpret it in various particular semirings, and in this case, in the confidence semiring, you notice that this one has better confidence than that, 1/8 or 1/16. And in fact, what that means is that I can construct a model in which I can maximize the confidence, and here it is, the model. And the big dashes mean that these edges cannot be present, are absent. And the small dashes means that it doesn't matter. So it's actually a whole family of models in which the confidence is maximized. So that's one of the things you can do with provenance analysis and interpretation in, say, the Viterbi semiring. Another example is this access control. So for this one, I actually took the phi, not the not phi. So suppose we know that these two tokens are public. So it's public that there is an edge from A to B, and public that there is no edge from C to A, and so on. But S and T are top secret. So now if you calculate the meaning in this semiring for the sentence, you get that, it's true, and this truth is public. But the provenance analysis allows you to say more, because you can look around in this polynomial, and both of them are going to be corresponding to alternative proofs. And in fact, this one is going to be, this monomial itself is going to be top secret. And this one is going to be public. So, it's true, and most people will know that it is true because P and R bar. But those with top secret clearance, okay, I'm really in the realm of BS here. Those with top secret clearance will know that there is an alternative proof, and maybe that's useful because maybe there's more confidence in that. Okay, so that's what we want to do with all this stuff. There's a lot more, and I'm already over time. An interesting problem is maximizing confidence not in one model, which can be done sort of locally, but are there ways in which we can maximize confidence in all models? And can this be done and in fact, for the fragment of first order logic corresponding to positive existential conjunctive, also known as conjunctive queries, this is in fact done by what's known as going to the core, not surprisingly, but that's if and only if the semiring has this property, which is called absorption, and there's much more to be said about that. There's a lot which I mentioned in my first talk in August, but I don't have time to mention now. When you add to the positive fragment least fixed points, and there are some interesting connections that I hope to explore. Most dramatically is to add least fixed points to the whole first order logic, and potentially other logics like mu calculi, etc. And there are some interesting connections with context-free grammars, but not for usual languages, but for languages of commutative words. What's a commutative word? That's a bag. So the order of the letters doesn't matter. So I'm sorry for running over.
Couple of questions? Yes.
In self-constrained satisfaction.
God, I wanted to say that.
Self-constrained satisfaction, there is a property which is very important, which is the idempotency of the multiplicative operation, because without that you cannot make constraint propagation. This property has some relevance in this setting?
Is not. So, do you mean idempotence of the addition, maybe?
No. Multiplicative.
So, for example, when you talk about cost, what corresponds to multiplication is adding cost. And, it just doesn't it's not that interesting to add cost and to say that 10 plus 10 is 10.
For instance, in the basic case, you get the max.
Yeah. So of course, this framework is general, and the examples you describe are particular cases. But the examples I found interesting from the database provenance and from what I talked about today do not have that particular. In the access control semiring, for example, and in all distributive lattices, this is the case. Yes, I should say, and I wanted to say that a lot of work with semirings has been done in the context of soft constraint satisfaction problems by Bistarelli and Montanari.
Thank you. Do you have a question? Just make a remark.
No, go ahead.
Okay, so just to make a remark to connect the provenance semiring work with other things which might seem surprising. So Rui presented a resource algebra which was for contextuality. Now, that was done with respect to probability distributions, but one can generalize that, and that's been a sort of something a useful generalization to any commutative semiring.
Right.
And then the operations there, which look like sort of the static part of process algebra, are essentially the relational algebra version of the standard database query language in this semiring provenance sense. So there's a rather direct connection.
So it's a way of doing resource analysis of normal logic without going to linear logic.
I don't think there's a connection with linear logic.
I was just, that's because this was drummed into my head for the last 25 years that, if you want to analyze resource usage, linear logic.
Right. I think the point I'm rather making is that there's a connection with things motivated by quantum mechanics, contextuality, and so on, and the operations that arise naturally here.
Did not have time to look at that, but I very much look forward to it. Yeah.
All right, let's thank Val again.